In the present video, current electricity part 2, we will be discussing the current flow through conductors, the drift speed of the electrons, another important term, the relaxation time. Then we will correlate the drift speed with current. We'll define the current density and obtain an expression for it. We have to see the mechanism of flow of current in a conductor. How does the current flow through a conductor? For the purpose, let's consider this diagram. Every conductor has free electrons in it. The electrons are in constant random motion. This random thermal motion, however, does not result in flow of current. The reason is the number of electrons which cross a section xy from left in a given time is equal to the number of electrons which cross the section xy from right. So as you can see in this diagram, the number of electrons moving towards right is equal to the number of electrons moving towards left across xy. So there is no net transfer of electrons across section xy. Symbolically, it is represented by these arrows of equal size. The number of electrons crossing on either side is 0. So that gives average random velocity of free electrons becomes 0. Mathematically, you can write average velocity u equal to u1, the velocity of first electron due to thermal energy, plus second, plus third, and so on. Average over all the free electrons is 0. Hence, the current I is 0. Even otherwise, we don't expect any current in absence of any potential difference. Now, let's see how does the current flow. For flow of current, we have to apply a potential difference. In this figure, we have applied a potential difference. V1 is potential on the left end of the conductor and V2 on the right end. We have V1 greater than V2. As a result, an electric field is developed from left to right because electric field acts in the direction of decreasing potential. Higher potential, lower potential, we have an electric field towards right. Since the electrons carry negative charge, they experience a force opposite to the direction of the electric field. So electrons experience a force against the direction of electric field. Electric field, higher potential to lower potential, V1 to V2 towards right. The force on electrons is from V2 to V1 opposite to the field, that is towards left. As a result, the number of electrons crossing xy from right exceeds the number in opposite direction. We know that electrons carry negative charge and they will move towards the higher potential. So left side, they experience a pull. As a result, there is a net transfer of electrons across every section of the conductor. See the diagram, you have larger number of electrons crossing from right as compared to the electrons crossing from left. We have also symbolically represented as a larger arrow, larger n, and the number of electrons n from towards left across xy exceeds the number n dash from left to right. So there's a net transfer of electrons, as we said. This causes the current to flow through the conductor. The same diagram for our reference. So when an electric field is present, each electron experiences an acceleration given by the ratio force to mass. Force is QE, or minus EE for electron, the charge is minus E. So this gives us the acceleration, where m denotes the mass of the electron. Between two successive collisions with positive ions of the metallic lattice, the electron gains a velocity component in addition to the random thermal velocity. Now this needs slight clarification. An electron is free. We are talking about free electrons. It undergoes collision with a particular ion. After that it is free. During this free time, it gains an additional velocity component in the direction of acceleration. Let us see how much is it. The gain in velocity lasts for a very short time, and the additional energy gained is lost in the subsequent collision. So between two collisions, the electron is free. This time varies for one electron to the other electron and so on. The average time elapsed between two successive collisions of an electron is called relaxation time. We denote it by tau. We have average time equal to tau 1 plus tau 2 plus tau n over n, where tau 1, tau 2, etc. denote the free time of individual electrons and tau the average time. In this average time, an electron gains average velocity Vd equal to, this is u plus at. U is 0 as we already calculated. A into tau, acceleration into tau. This is value of acceleration. We have a negative sign here. This negative sign indicates that the drift velocity of electrons is opposite to the direction of applied field. Opposite to the field as is indicated by the negative sign. The drift velocity is defined as the velocity with which the free electrons get drifted towards the positive terminal under the effect of applied electric field. Remember, the thermal motion does not cause current. The drift velocity causes the flow of current. The drift velocity is provided to the free electrons by external electric field. And this has a typically very low value of 1 millimeter per second, as we will discuss later. Now let's get to the expression for current in terms of drift velocity. Let us consider a conductor with uniform area of cross section A having n free electrons per unit volume and carrying a current I. See, remember the parameters. The area of cross section is A, the current is I, the number of free electrons per unit volume is n, and Vd is the drift speed of the free electrons in the conductor. Let us take any two sections xy of the conductor separated by a distance Vd. Vd is numerically equal to the drift speed. This is distance here, Vd, between x and y, and it is numerically equal to the drift speed. So this also is the distance covered by free electrons in 1 second. In 1 second, all free electrons between x and y will cover a distance Vd and hence drift past y. So these electrons, they drift past y, that is against the direction of current. You can consider this electron, if you consider the maximum distance which the electron can cover in 1 second is Vd. So all electrons which are present between x and y, they will cross y in 1 second. The current is given by charge per second, which means number of free electrons between x and y multiplied by E. The number can be calculated by number per unit volume, small n, multiplied by volume between x and y into E as already indicated. So we have N, the volume is area into distance, AVD into E. So that gives us the current as NEAVD. The expression for current density, what is current density? The current density in a conductor is the current per unit area of cross section of a conductor. The SI unit for current density is ampere per meter square current over area. Mathematically, current density J is I over A, or the vector J is current NEAVD over A with a negative sign because we know current is against the drift speed, equal to NEVD because A cancels out. The negative sign implies that electron drift is opposite to the conventional direction of current. And we have current as the scalar product of the current density vector and the area vector. This is the relation between, this is the expression for current density. You may subscribe to our channel CBSE 042 and also like the video by clicking the appropriate button. Should you have any feedback, write to ikg54@yahoo.co.in. You may visit our blog for notes and other videos. Happy learning and thanks for watching.